This video is a summary of what we've done on the playlist of the calculus of variations. So we started off by defining this integral here, I is equal to the integral from a to b of f of x, y derived by dx, and we said that that is called a functional. We then derived the Euler-Lagrange equation, which tells us that if partial f by partial y minus d by dx partial f by partial y derivative equals 0, then I is stationary. We then looked at ways of simplifying the Euler-Lagrange equation, and we were able to say that if there's no explicit dependence on x, then the Euler-Lagrange can be simplified to f minus y derivative partial f by partial y derivative equals a constant. And if there's no explicit dependence on x or y, then we can say that partial f by partial y derivative equals a constant. We then looked at the Lagrange test, and we said that if the range of integration is small, and if the sign of partial squared f by partial y derivative squared does not change on the interval ab, then we can say that the integral is a maximum if partial squared f by partial y derivative squared is less than 0, and it's a minimum if partial squared f by partial y derivative squared is greater than 0. We then looked what would happen if the solution to the Euler-Lagrange went exactly equal to 0. Then we could still evaluate I as a function of x and y only. We then derived the Jacobi accessory equation, which is a second order version of the Euler-Lagrange equation. We then looked at defining conjugate points, and we've seen that if u of x is a solution to the equation above, and if a is an abscissa of some point a on an extremal, and if u of a equals 0, then the roots of u of x equals 0 are the abscissa of points conjugate to a on that extremal. We then looked at the Jacobi test, and the Jacobi test helped us to answer the first part of the Euler-Lagrange test. The range of integration is small. So what do we mean by that? So in the Jacobi test, if we think of s of x as an extremal through some point ab for some functional, and if a dash is conjugate to some point a on ab, and if b lies between a and a dash, then partial squared f by partial y derivative squared, also if partial squared f by partial y derivative squared does not change sign in AB, then we're able to say that partial squared f by partial y derivative squared is negative, then I is a maximum. That should be maximum. Is a maximum. And if partial squared f by partial y derivative squared is positive, then that value there should be a minimum. A minimum. We then went on and we looked at an analytic method of finding the conjugate points. So if u1 of x and u2 of x are independent solutions of the Jacobi accessory equation, then for abscissa of points conjugate to a, we have u1 of x upon u2 of x equals u1 of a upon u2 of a. And then we're able to find those abscissa of the conjugate points by partial y by partial c1 divided by partial y upon partial c2 equals partial y by partial c1 by partial y by partial c2 at x equals a. We then looked at a geometric method for finding the conjugate points. So if the extremals through some point A have some envelope E, then the points of contact of the envelope and the extremal are the conjugate points to A. Then we looked at a couple of properties of the accessory equation. So we've seen that if u of x is a solution, then u of x does not have double roots. And if u1 of x and u2 of x are independent solutions, then u1 of x upon u2 of x either steadily increases or decreases as x increases. Okay, thank you for listening. If you enjoyed the video, then please don't forget to subscribe. Goodbye.